All right, guys, we're getting close to the end. We are on light. This is our second type of wave. And you'll notice by the slide right at the beginning that I'm calling this electromagnetic energy because light is a wave that moves in an electromagnetic wave. And I'm going to explain that in just a minute. But technically, all of the stuff we're going to talk about today is more accurately described as electromagnetic energy. So let's go ahead and get into it. Just like sound, there are a few characteristics that you need to know about light. First of all, light is a transverse wave as opposed to sound, which was a compression wave. In addition to the fact that light is a transverse wave, it can travel through a vacuum. That's because it's not a mechanical wave. It is an electromagnetic wave. That's the other category that we talked about when we talked about mechanical waves. So remember, a mechanical wave requires a medium because it uses the particles of the medium to propagate itself. Well, light, electromagnetic waves, light is self-propagating. It drives itself. And to make a long story short, the way that light propagates itself is that it's made by basically vibrating an electron, and that electron is electrically charged. It's an electrical field. Well, it turns out when you move an electrical field, it's called flux, that moving electrical charge creates a magnetic field. And this is another branch of physics that we didn't talk about, but I'm just giving you basic details of what we're talking about. This picture shows it, this GIF shows it. The electric field creates a magnetic field that is perpendicular to that electric field. But then the reverse is also true, that as the magnetic field moves, because the electric field is moving, it also in turn creates another electric field, which creates another magnetic field, vice versa, and it keeps going back and forth. And that's basically a really dumbed down and probably slightly incorrect version of how electromagnetic waves are self-propagating. They drive themselves. They do not use the particles of the medium to propagate. The electric field propagates the magnetic field. That magnetic field repropagates an electric field, etc., etc. That's how light can travel in a vacuum. Now, it doesn't have to, remember. It doesn't have to. Light can travel through different media, water, air, glass, whatever we've got. But in those media, it actually slows down as the density of the medium increases, and that's opposite of sound. Remember, with sound, as the density went up, the speed went up. Well, now with light, if we go into a more dense medium, it actually slows down because those molecules just get in the way. It doesn't use the molecules to propagate itself. It can go through them, but it takes more time to do that. Speaking of slowing down, you need to know, this is very important, that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. And this is a really, really important thing to remember. 300 million meters per second, and that's an approximation. I'm going to say 300 million. I'm going to require you to remember 3 times 10 to the 8th, which is 300 million. It's actually 299,792,458 meters per second. That's about 186,000 miles per second. So the speed of light is a really interesting thing. It's one of my favorite things to talk about in this class. So as far as the speed of light, 300 million meters per second, as you can see. What's interesting about light that many people don't realize is that it looks instantaneous. It seems to reach our eyes practically instantaneously. When you turn on the light, boom, everything shows up. But that's not actually the way it occurs. And if we could slow light down, what we would find is that when we turn on the light, it actually takes a little bit of time to reach our eyes and to illuminate everything in the room. It's not instantaneous. It's PDQ, which stands for pretty darn quick. It is pretty darn quick. Like what I just showed you was drastically slowed down, but it is very, very fast. Across a room, which is sort of what I'm depicting here, it'd take approximately 15 to 20 nanoseconds to move across a room. Now, you probably don't know what a nanosecond is, and just as reference, it takes you 200 million nanoseconds to blink. So there's something for you. Let's see if we can get a little bit closer to understanding how fast light is. This is the Earth. Obviously, you should know that. Um, Light is 671 million miles per hour. Never gone that fast. Number that big doesn't really mean anything to me. Okay, 186,000 miles per second. Still too big of a number. Doesn't really mean anything to me. So to get an accurate representation of really like approximately like what are we doing? How fast does light travel? Well, the circumference of the Earth is really, really big, as you can imagine. And it takes us 24 hours to go around the circumference of the Earth, because that's how long it takes the Earth to rotate, which means we're moving at about 1,000 miles an hour, all right? Which is super fast, but it isn't anywhere close to the speed of light. The speed of light, if you were moving at the speed of light, you could move around the circumference of the Earth in 1 second. And actually, you could do that 7 times. Yeah, it's that fast. 1 second, 7 times around the circumference of the Earth. 1, 2, 3, 4, 5, 6, 7. That's how fast light is. Light is actually so fast that, to be honest with you, don't tell anybody this, but it's kind of impossible to measure. Now, there's a lot of assumptions that go into measuring the speed of light, and I don't want to go into those right now. But you need to know that it's actually impossible to measure the one-way speed of light like we do for everything else to measure its speed. It's too fast. We have to bounce light off of something and make it hit something else, and we have to assume that it's the same speed going both directions, and we don't actually know if that's true. But this is the accepted figure for the speed of light. Physicists accept this. 300 million meters per second, approximately. And that figure hasn't proven us wrong yet. It hasn't let us down. As another example of the speed of light, at that speed, 7 times around the circumference of the Earth, 1 second to do that, really, really fast. At that speed, if we shrink the Earth down, here's the sun, here's the Earth. The sun is actually about 93 million miles from Earth. And at that distance, light, moving crazy fast, that speed 7 times around the circumference of the Earth in 1 second, light moving at that speed actually takes a certain amount of time to get here. It's about 8 minutes. Yeah, it takes light from the sun 8 minutes to reach the Earth, which means this: if the sun blew up, you wouldn't know it for about 8 minutes, because the speed of light is technically the speed limit of the universe. Theoretically, nothing can go any faster than that. No information can travel faster than that. So if the sun blew up, you wouldn't know. You know nothing for 8 minutes. Which brings us into another topic called a light year. You need to know about light years. A light year is a distance. It's not an amount of time. People see light year and they think it's an amount of time. It's not a time, it's actually a distance. It's the distance light travels in 1 year. Now think about that. Light goes so fast, you can go around the circumference of the Earth 7 times in 1 second. And at that speed, it takes 8 minutes to get to the sun. Imagine doing that for a year. Going that fast, day in and day out, minute after minute, hour after hour, for an entire year. If you did that, you would travel a distance of 5.88 trillion miles, which I know is a big number, but nobody really understands how big it is. It's so big, we can't really wrap our brains around it. So what we can look at when we talk about light years is we need to know that light years is the sort of meter stick that we use when we measure distance in outer space. We can't use meter sticks anymore. We can't use miles or kilometers. As you can see, 5.88 trillion miles really doesn't cut it. We have to measure things in light years. So I'm going to show you a couple of stars. Alpha Centauri is actually the star that's closest to us, closest to the Earth, aside from the sun. Closest star to Earth aside from the sun, and Alpha Centauri is actually 4.4 light years away from Earth. Here's what that means. Light traveling from this star, moving at the speed of light, takes 4.4 years to reach here. Light that you see coming from this star tonight left it over 4 years ago. That was December 2016, y'all. That's kind of crazy. Like, think about what you were doing 4 years ago. You were like, what, in the 8th grade? Light from that star left it at that time, and since then constantly has been moving at that crazy fast speed, and it's just now going to get here. That's how far away that star is, and that's the closest star to us. We can go farther out If you look at this constellation, it's a very, very famous constellation. Here it is. I'll highlight it on your screen. It's called the Big Dipper. And in that constellation, there's a star called Merak. Merak is not 4.4 light years away. It is 80 light years away. 80 light years away, which means, drum roll people, light left this star 80 years ago to reach this Earth tonight so you can see it. That was 1941. That's World War II. In World War II, light left this star and has been traveling here ever since then at the crazy fast speed of light just to reach you tonight. Which means, in the middle of this, I want to say this. You probably figured this out already. When you look at the stars, you are looking into the past. We cannot possibly see the stars the way they look right now in this instant because light doesn't travel that fast. I can't see it instantaneously. These stars are so far away that all we can do is look at the stars the way they looked at some point in the future, depending on how far away they are. Here's another one. This is a very famous constellation called Orion. And in Orion, there's a star called Betelgeuse up on the right shoulder of Orion. You ready for this one? Betelgeuse is 643 light years away. Light left this star 643 years ago in the year 1378 just to get here tonight so that you can see it. That's pretty far. It's not even the farthest star. Here's some other astronomical distances that are noteworthy. There's a huge star called Sirius that is 8.6 light years away. Vega, another really big star, 25 light years away. Arcturus, one of the biggest stars in the nighttime sky, 36.7 light years away, almost 40 years for that light to get here. The Pleiades open star cluster, which is actually what you see here, 444 light years away. Antares is another big star, 619.7 light years away. You might have seen pictures of this nebula before. It's called the Horsehead Nebula. Y'all, it's 1,500 light years away. 1,500 light years. Light left that thing 1,500 years ago. The Milky Way galaxy, it's a galaxy that we live in. The distance across that thing from one edge to the other is approximately 100,000 light years. If you're traveling at the speed of light, light takes 100,000 years to reach from one side of the galaxy to the other. The Sombrero Galaxy is the farthest thing we know of, as far as I know, which is, I'm probably wrong, in our galaxy. Y'all, it's 29.3 million light years away. We're seeing this galaxy, if you look at it tonight, you're seeing it as it looked 29.3 million years ago. And this is all because of the speed of light, which is the fastest thing we know, but on the order of universal distances, it can be pretty pokey. For that reason, it's impossible for us to see things as they look right now. We have to wait for the light to get here from us. Very similar with signals we get from spacecraft. Right now, we're looking at things that are on Mars. We've put some spacecraft on Mars. We had a helicopter just make a flight on Mars. Well, those signals are sent by radio waves, which travel at the speed of light. We can't get those signals for about 20 minutes because of how far away Mars is right now. So that's the speed of light.